Hello everyone, I'm Changxi from National University of Singapore, advised by Trevor Carlson. And today I'm going to present our work, the Sparsity-Aware LazyGPU architecture. So before I go to our main session, let's talk about some background. So as we all know, the demand for computational power is growing rapidly recent years. As we can see that as about 10 years ago, we think that training a neural network like VG16 is a very huge workload. It requires like one extra flop. But now, if we think it back, we found that comparing with training GPT-4, it's just a smart deal. So what does it mean? It means that we require high-performance GPUs to satisfy the demand of computer resources always. We want to continue want higher and higher performance GPUs. And now, lots of companies are working on that. As we all know, NVIDIA, they have their Hopper architecture. And also AMD, they have their MI series GPUs. And also Apple, recently they proposed their heterogeneous processor, combining CPU and GPU together, and also Intel and lots of companies. I don't want to list all of them. So the question is that are GPU workloads, is it compute or memory bound? This is a question. And there is a paper published last year on ISCA' macro called AI and the Memory Wall. In the paper, they listed the trend of the bandwidth and the peak performance, peak follow-ups over the years. And if we see the trend, we can find that especially after the introducing the Tensor Core, the computing capability is rapidly increasing. But we found that the memory, they can't keep in pace with that. So let's give one example to say what will GPU workloads executing if it is totally memory bound. So here is an example. It's just a portion of the matrix multiplication kernel. We will first execute 2 load instructions. We require 8 cycles to issue these memory requests. And then we do some independent instruction to try to cover the latency of the memory request. But since that we can't do it forever, so finally we still need some ALU instruction that depend on these memory requests. So then let's give an assumption that all the memory requests, they are conflict with each other. It may be conflicted by like bound conflicts or by MSHR busy or other. So if it works like this, we can find that assuming that we have 2 wavefronts, wavefront 0 and wavefront 1, and since that this 20 cycles ALU is totally independent with these memory requests, so we can still executing it. We are waiting for the memory request to be written. However, the bad news is that since they are all conflict with each other, so we need to wait for the first memory request to be written. Then we can start serving the second one. And the wavefront 1, although we know they are totally independent with each other, but since this underlying hardware constraint, so we should wait for the wavefront 1, wavefront 0 to finish their first 2 requests. And then, since that in wavefront 0, these 128 cycles ALU, they just require the 2 memory requests to be written. So they can start in parallel to executing these ALU instructions. So wavefront 1 start to process its first memory request, and then the second one, and then we finish the whole load. So it requires about like totally 388 cycles to finish the whole loads. We found that many GPU workloads, they are memory bound. The case side here is that the loads issued in, if we issue them in program order and don't optimize them for the criticality, which means that it just issue them in the program order. So it can cause some problem. For example, here we can see that in actually, if we say these ALU instructions, we found that it just requires the second memory request to be satisfied. Then they can just execute it. However, it is blocked by the first memory request. And another thing is that even we don't deploy it like Yifan 1, we still need to wait for all the memory requests to be finished. So our urgent memory request is blocked by the non-urgent memory request. So how to solve it? So we're thinking that how about we issuing these loads with high critical-reality to improve the utilization and increase the throughput. But how? So which one is more important, which one not important? It's hard to decide. So our insight that, okay, if we don't know, maybe we just delay issuing them, and when we really require it. If we really require it, which means it must be very urgent, right? It's like that when we are working, there are two kinds of people. Some people, they make a good plan, always do it in advance. And some people, they just driven by the deadline. And every deadline comes, I should work on it. And every deadline comes, work on it. We all know if you have small workloads, yeah, of course, the first kind of person, they have more work efficiency. But if you have like 100,000, even millions workloads come to your mind, maybe work by demand can be better efficiency. Okay, so then we give an example to say how GPU with lazy car works. So it is the same workloads, and we found that since we issue them by demand, we found that only the first memory request of Yifan 0 and Yifan 1 they conflict with each other. And luckily, since that we should executing these independent ALU instructions, so we just luckily make the remaining memory requests that are totally not independent with not conflict with each other. So we can see that in this smart demo, we can reduce the runtime to 348 cycles. So then let's go to our methodology. So our methodology, this is an example to show how our methodology works. So we have two load instructions to load the data to register 0 and 1. Then we use MAC. MAC is multiply accumulation instruction. It will multiply register 1 with 0 and then add the value to register 2. So since that we are lazy, so we just generate a memory request, but we won't issue them to the memory system. We will holding it. And when we are really require it, which is like in the MAC instruction, then we issue them. And since at that time we have some time to think about more, so in our architecture we will first load some 0 masks when we are executing this load instruction. So then when we really require this value, then we know that okay, this value is 0 or it's not 0. So if it is 0, which means it's just 0, so we don't need to really load the data, and we just eliminate this memory request. And another thing is that since they are multiplying with 0, as we all know that any value multiplying with 0 is just 0, so it doesn't matter it is 1 or 2 or 100, it doesn't matter. So we just get the 0 results. So, however, here you should know that it's different with fetching 0, because you don't know that if this value may be required by the following instructions. Yeah, for example, maybe after MAC, it will be used by the add or some other. So the value might be used. So here we're just suspending the memory request. And when this target register are overwritten means that this value we can be sure, hardware sure that this value won't be used forever. Then we eliminate them. So this is the whole workflow or methodology. This is our microarchitecture. We mainly change 3 parts. The first is that we introduce a new unit to enable the lazy execution core. So it can enable really issuing the memory requests. And then we combine the lazy core with 0 cache. So we have a 0 cache. So it can rapidly validate if there is 0 or not. And then we can eliminate these corresponding memory requests. And another one is that we combine lazy core with ALU. So then we know that if this value really have no effect on the final results or not, like multiplying with 0 or AND with 0. So this is our architecture. And then we go to our evaluation. So we use MGPU sim as our simulator to simulate this architecture. And the benchmark we use, we evaluate all the benchmarks provided by MGPU sim. We also add 2 new benchmarks. One is ResNet, and one is large language model, Llama 7B. So since that as we all know that large language model, they don't use ReLU, which means that naturally there isn't any 0, but we want to evaluate some 0. So then we use one paper, Wanda. It is published in last year SLR, introduce some weight sparsity to evaluate our methodology. Since that for large language model, one kernel is, even we want to simulate one matrix multiplication, it may cost about even 1 year. So it's impossible to simulate the large language model. But we use a simple methodology called the photon to speed up a simulation. So then we can get the result of large language model. So here is an advertisement. So the photon is also our work, and it has been integrated into the main branch. So welcome to use it to also evaluate your results if you want to use it. It is already in the main branch. Just one flag you can use it. It's very easy. And before I go to the result of LazyGPU, let's first see the lazy car. Lazy car is our base idea, and we found that for the lazy car, we can have a lower memory access latency compared with the baseline. You can see that along with the time, lazy car usually have a lower memory access latency. So why? It's because that we're holding this non-urgent memory requests, which means that they want to compete with the urgent memory request. So that's why. We also evaluate on a varying number of wavefronts to see. We found that with the larger wavefront count, so why the latency is increasing? Because that all the memory requests are waiting to be served. So that's why their latency is continually increasing. And lazy car can mitigate it. So lazy car is mainly, we can't reduce the latency to access one bank. It's impossible because it's hardware. But since that we're reordering the memory request order, so which means that we can reduce the queuing latency to waiting for the request to be served. So that's the performance where the performance comes. And so that's why this comes, and it's because that we prioritize it. And any other benefits, as we discussed it before, since we are waiting, so waiting means that we can think more. We mean that we have large look-ahead distance to optimize the memory requests. Like maybe they fetching 0 or they don't have any effect on the final result, so we can just delete it. And we evaluate on these mini benchmarks. We're first using the default inputs, which means that it just have a very small 0. It's depending on their inputs that we don't know. And we can find that we can get about 8% speed up performance improvement on average. And we also introduce some 0, and we found that when the sparsity is 80, we can get a very high speed up. And there are some results of the large language model, like perplexity is. So we use the weight sparsity, Wanda. So why we just evaluate 60% is because that when it is larger, the perplexity will be very high. So it's meaningless. So we found that when the sparsity is 0, which means that just the normal inputs have very less 0, we can still have like 80% speed up. And if you have zeros, it's unstructured 0, we can have about like 2 times speed up compared to the baseline. So this is the conclusion. So this is the first GPU architecture designed on lazy execution car. And we also use zero cache to identify and skip fetching the zero value, and we also use limited dead memory requests whose value have no effect on the final results, like multiplying with 0. And we get a very high speed up when there is sparsity, even without sparsity. And thanks, and welcome question.